So the topic we are going to cover today is periodicity 1. And periodicity 1, as you can see, it is the very first topic of Senior 5 Term 2 as far as the syllabus book is concerned. So generally, the topic is periodicity 1 and it has 3 subtopics. And I want us to conclude the first subtopic today, even if I remain on the call alone. For me, I'm completing it today, and that's the periodic table. So the first subtopic is the periodic table. Then the second subtopic concerns period 3 elements and diagonal relationships. Yeah. So even period 3 elements have some sort of relationships, unlike some of you. So that is the second subtopic. Period 3 elements and diagonal relationships. Then the other last one is the chemistry of group 2 elements. And I want us to be using just a lesson and a long one. So this one will always be covered in the night and not during day. That's if we are to have a long session. So this will be covered later. Very few schools have reached that, as far as I know. But most of you people are around here, period 3, and most of you are done with the periodic table. But this topic of the periodic table, the subtopic, is very important in that it's what lays the foundation of the others. And I would be very happy if someone at least takes a screenshot of that to understand what we are actually going to cover today. Yeah. The good thing with the introduction of this first subtopic is that you need to do the reading on your own. Yeah. The tutor must begin from somewhere here. And that is all. So basically, in this topic, I may not write the learning targets today, but if I may, then of course we usually extract them from the syllabus book. This. We are going to talk about the historical development of the periodic table from the very first design, the Mendeleev, or you can call it Mendeleev, whichever, to the Mosley's atomic concept. Then after that, we shall look at how the modern periodic table is organized. Yeah, it is very key to look at that evolution, the evolution of what? The periodic table. And identifying similarities in blocks, groups, periods. I taught these things in electronic configuration. So if you have not visited that lesson yet, you're going to find it a bit hard to understand some of the terms like blocks and some other things. These are things that we literally gave time in that lesson. You visit it because I believe everyone here has access to the drive. So feel free to access it. Then the other part, which is the most important, is predicting trends. Exactly in properties such as reactivity based on element positions. By element positions, they mean these things of across a period, down a group. You've been seeing those things, but I'm going to try my level best way to illustrate. Now the last part is concerning the meaning of periodic properties such as atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, electropositivity, and so on. And this is what I'm supposed to really give time today. Yeah, that is what I really want. You see, these things are supposed to be given time. Why? When we do our best and talk about them well today, the next lesson of thermochemistry will be a good one. It won't disturb us at all. Yes, if we give them the time they really deserve. The lesson of thermochemistry will be the best. And those other future concepts, when we begin the group 2, group 14, group 17, and so on. So, kindly stay calm. That's all I want to cover today. I'm not going beyond this subtopic of the periodic table. Okay, now to be organized, it's okay. Let me just have a summary of what we are supposed to cover today. So the lesson targets, the very first one is the historical background. The very first one is the historical background. The periodic table. Then we are supposed to look at how the modern periodic table is organized. Then I think after that, we can now begin periodic properties. But as we talk about periodic properties, a lot of things are needed to be cited out. Yeah, because if you're to look at the periodic properties, you need to appreciate what they mean. So you need to know about their meaning. Then the other thing, you need to know the trend in variation. Of course, a trend shows how things are varying. But of course, as you're looking at the trend, we concentrate on two things: across a period and then down a group. There are people who are hearing of the periodic table for the first time, and I will respect that. How someone may be asking, why are you really saying across a period and down the group? Why not the reverse? Yes. So let me tell you that. So look at this. This is now the examinations periodic table, the one they usually give out in exams. I remember talking about it in those lessons we had those days in the beginning. So we have the groups, and these are the groups. These ones you see. The 1, the 2, the 3, the 4, the 5, 6, the 7, the 8. Those are the groups. So when you look at groups, are columns. When you look at the groups, they are the what? They are the columns. So if you're looking at a column, of course a column moves in that direction. You get? So it's supposed to be down a column, down the group. Then the periods are these ones in green. Yeah? Those are the periods. Like, for example, the whole of that is a single period. So periods are rows, yeah? And because of them being rows, it is always across them, yeah? From left to right, from right to left. So for them, they are rows. That's why we use the word across. And since these ones are just columns, that's why we use the word down. Understand? So it's supposed to be across a row like that. Then for these ones, it's supposed to be down a column. Exactly. So hope I'm understood there. We proceed. Then the other thing concerning the periodic properties, we need to know the explanations of the trends. So those are the things I want us to look at today. Whether I finish them on Tuesday, for me, I'm not leaving this call until I'm done. The only thing I can do for you is maybe to give you a break, then we get back. But even if you don't get back, for me, I'll proceed. So explanations of the trends. So I'll need someone who is going to be reminding us to take the screenshots every time we are done with the page. So we can start. Historical background. Now, I'm a chemistry teacher and not a history teacher. So don't expect me to take you through the historical background. That's some sort of disrespect. However, I have it in my notes. I told you I'm writing my notes, which I will release with time. That will be, of course, during Christmas. That's when I'll release my notes. I believe they will be fully ready. Yes, I don't want it to disturb me. Okay, so these are our notes. They are ours. So, as you've realized, this is chapter 4, topic 4, and it's what begins senior 5 term 2. So it's basically periodicity 1, and the subtopic we are handling is the periodic table. So concerning the historical development or background of the periodic table, I'm not going to go through these things, but I want you to be good people. How? You're going to take a screenshot. I'm going to give you that chance. Look at what Prout did. Look at when. Look at how Dalton, how this one, I don't know the pronunciations, and I don't want to pronounce them. People may have different pronunciations and people may laugh at me, something that may demoralize me. Then you look at the Canizaros, and when that happened, look at this other year, look at Newlands. So all these are people, eh? and their respective years if mentioned. So this is history which you just need to read. Yes, which you just need to read as a person. Where you really want to go so deep, use the internet. But this is the historical background which you just need to appreciate, but it's not examinable. Yeah, it's not examinable. But you can just read it just to know the stories, and then after you forget them. So it's all about appreciating that the periodic table actually has a historical background and nothing much. Yeah. Here showing you the sample, they were talking of the similar properties. So here, I will shift this to diagonal relationships. Yeah, so don't worry. Diagonal relationships, that's where we look at similarity. Yeah. So we shall see that as we are handling period 3, anything to do with similar properties. We shall see that under diagonal relationships, and that is under period 3. Don't want to leave anything unturned. Under period 3. So you continue reading the story. See, these guys are still here. Newlands even had a law which we will read. Then later, in this other year later on, a Russian chemist came in. You can see Dmitry Mendeleev, very important man in this, because his name is even somewhere in the syllabus book. But these are just stories to appreciate, but are not examinable. So you find textbooks, those will be using the textbooks on our Google Drive. You find those books having V here. Have it in mind that those people, double F and V, mean the same thing. Yeah, they have no problem with that. Just like most counties in the country, Uganda, have no problem with L and R. So those people, the same thing. V and double F, it's like the same thing. One is a letter, the other is a pronunciation. So replacement is almost negligible to them. So I don't want you to find other things and be like, Dr. Pock gave us different names. So look at what Newlands improved and what he said. These will be your stories. So I will allow you to take that screenshot so that you have a basis of reading. Hope the words will be clear enough. You take that screenshot. The people who have taken the screenshot, is it clear enough? Hope it is. Okay. Now, these were the improvements on the periodic table by Newlands. You can also read through them. The good thing you're taking screenshots so they can guide you meanwhile. So even have an illustration of the improvements that Newlands did. Yeah. So you realize that the improvements of Newlands led to the output or to the presentation of Mendeleev. You will enjoy the story. I don't want to say it here, but have it in mind. Different people came working together. The other dies, the other one takes over. This one leaves a legacy, the other one continues from there in different years until a final modern one was produced. So you will read those stories on your own concerning the organization, historical development, or historical background. Hope that is okay. Then the other thing is about the unique position of hydrogen, which is very clear. And still, those who attended electronic structure with me, whatever is here is just obvious. Yes, the confusion is only here. Look at this periodic table they give out in papers. I want you to look at this purple color I'm going to use. Are you seeing here? This is group 1, as you can see. It is group 1, but we have hydrogen. When you look here still, this is group 7, and we also have hydrogen. You understand? So because of the same element having more than one position on the periodic table, that's what they are talking about under unique position of hydrogen. So don't overthink. It's all about hydrogen occupying one or more, or hydrogen occupying 2 positions on the periodic table. So when I come here, this will be also your task. Read through. It's not much, but that's its basis. You get the point? So you can also take that screenshot and read through in your free time. Someone is like, are they examinable? No, you read through and appreciate. I've told you these are things you just need to appreciate. Okay. Now, still, remember the notes are supposed to follow the syllabus book. So whatever the syllabus mentioned, we had to write about it. You get the point? So here we have the modern periodic table. Our notes, copyright reserved. The modern periodic table, and we are interested in its structure. As of now, we are not yet sure of which periodic table you people are going to use. You understand? However, I want you to learn that the current periodic table, or the modern, leave alone this one they provide in the examination. This is not the modern. This is how the modern looks like. You're going to see it here below. That's how the modern one looks like. And if we are to count these ones, if we are to count the groups, let me show you something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. According to the simple sketch we have, this was some sort of extract, and that's what they only got. But we've stopped on 16. But if someone has very nice eyes, they are clearly seeing, are you seeing this Chi group here? Are you seeing that it has these 3 portions that weren't catered for? But let's say we Isaac, and for us we want to count the real number of columns without looking at this anomaly here. Let me use blue ink. Let's count. We get any period. Let me choose this period 4. We agreed the groups are the what? Columns. That's why we said down a column. Then this way down, we are having the periods, which are the rows moving in that direction. So I've said let's consider the 4th row, or the 4th period, and count to find out what is the exact number of columns here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Are you seeing? So in the real thing, the columns are 18, isn't it? Because whichever element I've crossed is present in its own column. So the modern periodic table that we have, the modern periodic table has 18 groups. You get? And when we check the syllabus book of you people, see your curriculum is still very funny, and you're supposed to appreciate that. That means being the first cohort, you're going to be favored in one way or the other. So you just keep following that confusion until you people get done with senior 6. Now, when you look at your syllabus, I want to show you a secret. In the old curriculum, this is not how groups are supposed to be written. As you can see here, they use 2. This is not right. You're supposed to use Roman numerals, something like that, group 2, or like just that, group 2. That's how it's supposed to be written. But even when we proceed, you see this is just periodicity 1. I'll be talking about this in tomorrow's facilitation. When you go to periodicity 2, I think it's topic 14. Let me check something here. Not topic 14, it's topic 11. Where is topic 11? This topic, this is topic 10, topic 11. It is here. Are you seeing this topic? It's topic 11. Are you seeing how they are calling group 14? They are using 14, but this 14 in the old curriculum, it was group 4, which was supposed to be, or which is supposed to be written like that. Then, the next topic after group 14, are you seeing? They called it group 17, and everywhere they were using 17, 17. So, we are not yet sure whether you people will use the modern one or the old one. But chances are high that we'll have to use the other old one. After all, it's what is most common when especially electronic configurations are being taught. So because dealing with the modern one may be a bit hectic for students, after all, it's having a lot of unnecessary elements. But all these can be dealt with. The most confusion is just there in the middle. And that's what you have to know. The groups are increasing in number because of these transition elements. Nothing else, these ones you're seeing. I talked about those transition elements in that lesson I'm talking of. But if you people have a keen eyesight, things are the same. Group 1, group 2, this is group 3, group 4, group 5, group 6, group 7, group 8, or group 0. The confusion is just there in that region of the transition elements, if you recall that is the region. So this modern periodic table shouldn't confuse you. I'm going to give you a technique that you're going to use to master them very fast. And these things should not confuse you. Are you seeing this? They are telling you that just below the periodic table, we have some 2 rows, which are so specific. So they are telling you that the periods are ending on 7, like the real rows end on period 7. But there are other 2 extra rows where we have what they call the lanthanum series and the actinium series. Those are why your teachers don't talk about this. It's not necessary. What I'm doing is to respect what the syllabus said. And I hereby tell you these are things that are supposed to be just mere appreciated. Don't stress your brain, but be like, there are some other extra 2 rows below the periodic table after period 7, the lanthanides and actinides, or the actinium series and the lanthanum series. Just that. No one is going to ask you. But have it in mind, it was part. That's what we do in Africa. Follow instructions and move on. Okay. So, concerning the organization, it's so easy. It's understandable if you attended my lesson on electronic configuration. All the things here we are talked about, you're going to come across these things of nihonium, moscovium, tennessine, organeson. That you just appreciate it. No one is going to examine you about organeson, no one. But you just read and simply appreciate. You can see the modern one has 18 groups, and the periods are 7. The other things coming last are very weird things. You see, they are talking of the lanthanum series or the lanthanides and the actinium series or the actinides. For me, I like those words. I don't know why. Okay, you take that screenshot. You first take that screenshot, the whole of it. Then I also expose the whole modern periodic table. You also take it. Just to appreciate it. I don't want you to lose vibe for the lesson before we begin the real work. That's why I'm simply guiding you on how you're supposed to read them. So I pray we maintain 10 less than the number we have before the lesson actually ends. So you can also take that, which is more clear. That's the modern periodic table. Modern periodic table. And we have agreed the confusion or the increase in the number of groups is brought about by that transition space. The space of the transition elements. Yeah. Okay. Think I can go. Now they are talking of this thing, which I'm not going to teach. I taught. They are saying classification of elements based on electronic configurations as SPD and F. I taught SPD and F. You see why I record my lessons? Because someone might have forgotten that. So go to the drive, look for atomic and electronic structure and electronic configuration or electron structure folder, and you see all this work. I'm not repeating it. So I'll say, okay, let me give people directions so that you can follow them. Yeah? You go to the chemistry, go to our drive under chemistry. You go to senior 5 term 1 work. I don't want you to say we never saw the video. Senior 5 term 1 work. Then go under atomic and electronic structure. Atomic and electronic structure. Then after there, you go to you have agreed. I taught this under electronic configuration. Then your destination is lesson 1. Yeah. Lesson 1. When you reach lesson 1, you've reached. That's where everything is. I talked of all these things having 4 main blocks. I talked of the S block elements. You saw them. I talked of the P block elements. Or I talked of the P block. I talked of the D block, even where they are located. Now, these ones shouldn't scare you, eh? These ones shouldn't scare you. When you see they are saying first transition series, second transition series, third transition series, these ones should not scare you at all. However, they are giving you the directions, but this one is under a topic. I want you to look here. Are you seeing this topic? It is called the D block transition elements. So as we are talking of transition elements, that's where we shall talk of the transition series. So you be strong. Don't lose hope. So that one shouldn't stress you. It will be taught under what? Under transition elements. So you just need to be with us until we reach transition elements. Then I also told you about the F block and where it is. Yeah. And I remember telling you people, if you recall very well, that the F block elements are these ones. That F block, I remember telling people, I remember we drew such a structure for the periodic table. Those were with us. We drew such a structure for the periodic table. We had such a structure. Then I remember telling people these things in this chi block, this chi block that looks far away as if it's on its own things. I remember telling people that that's what we call the F block. In that very lesson, even when you look at the real periodic table and look somewhere here down, are you seeing these people? These ones, those two rows, they are doing their own things. They are this side alone. It's like they're in their own world. But this is all supposed to be just mere appreciated. That's why I don't want to talk about it beyond 9:30. That will be a wastage of time. So, and these are the things in the F block. I told people that that's the F block. And that's where we find the other two things. The lanthanides, actinides, or the actinium series, and the what? Okay. So just like you can see here, they are telling you divided into two. You get the actinides and the lanthanides, or the lanthanum series and the actinium series. These ones. So if you feel like you really love the subject, you can go through it. Can go through it. These things I taught, S block, D block, P block, and I told you the F is somewhere here, as if it's in its own world. But that lesson has it all. Then even those who recall, I talked about this same thing. Which ones are the metals, which ones are the metalloids, which ones are the non-metals, if you recall. So we shall also find that in the same lesson. Trust me when you watch that lesson and come back here to read, these things will be very obvious. And all of you know that metals are good conductors, the non-metals are poor ones. Then of course the metalloids are just their intermediate in those properties. So trust me, these statements are very clear. I tried to make sure that they are so clear to anyone who will be just reading them for appreciation. Okay, that's why for them they are calling them what? Semiconductors, because they are just there between being good and being poor at conduction. So semiconductors. Now, this is the real thing. This is what I'm supposed to teach today. And it is exactly 9:30, as I said. That's what I'm supposed to teach today. So you take this screenshot. Where did we stop? You take that screenshot, it will guide you. We take that screenshot. After that screenshot, you take that. And by the way, this lesson should be a lesson to you guys that if at all I taught something in a given lesson, that's why I record my work. I will never repeat it. I'll just always refer you. I'll just keep on telling you, go to that lesson, visit this lesson like that. And I'll never repeat myself. So we are handling this now. Periodicity of atomic properties in the periodic table. So let me give you some sort of introduction before we actually read through. I'm going to first give you some sort of introduction about periodicity generally. So we have said anything to do with historical background and organization of modern periodic table. Those things of metals, non-metals, metalloids are part of the organization, yeah? The modern periodic table. So I believe these ones have been handled. And what have we agreed on? Screenshots have been taken. Screenshots have been taken. And internet, especially YouTube, yeah? There are some good YouTube videos on the historical background of the periodic table and the organization, yeah? And YouTube have been advised. So even those who don't want to read through those things as I've advised, you can just go to YouTube. Yes, go to YouTube. Even your syllabus book is clear that simulations are supposed to be used in your training because most of the learning is supposed to be student-centered. Historical background, put it in as it is, or historical development. Organization of the modern, put it in like that in the YouTube search bar. They bring videos, you watch. You make a few notes, you proceed to other examinable things. Get the point? So, I'll come here to my lesson targets and I'll tick. Yes, I'll tick historical background, I'm done. I'll tick the organization, I'm also done. Yes, you have the guidance, you have what to read, you have the directions. So basically, I got to concentrate on target 3, which is the last target but taking us forever. So tighten your seat belts. Okay. We are saying that the elements of the periodic table have properties which vary as you move from one element to the next. Now, I want to tell you something. We are saying elements of the periodic table have properties. So these properties, first things first, they are the ones they call periodic properties. I want you to listen. They're the ones they call what? Periodic properties. Now they are saying from one element, I need your attention here. They are saying from one element to the what? To the next. In the periodic table, assume we are having an element here, x. To look for the next element after x, you may either move in that direction and go to your y, or you can move in this direction down. Still to y. You get the point? So this one is still the next element after x, even this one is the next element after x. I'm interested in these directions, either moving to the right or downwards. So as you're moving in the same, like moving from x to y, that's what they call across a what? Across a period. Because you people are aware, periods are the rows, groups are the columns. Period, group. Then from x to y, that's what they call down a group. So why am I trying to show you this? Whichever thing we are going to discuss today, we are going to be interested in two things. How does the variation happen down a group? And how does the variation happen across a period? I want you to listen. The introduction to periodic properties is going to be very key, as far as these are things that disturb most Form 5s in the country. So you gotta listen and teach the rest of the country. So, some of those periodic properties that differ as you move from one element to the next, I'm going to just give you one. I'll just say such as their size, because I've not yet started listing the real statements, the real chemistry. This is still English. But this word size, I will even put it in red and put an X, trying to show you it is not an accepted word in chemistry. The word they accept is the word radius. But as I've said, I'm just speaking English. Now, this is the good news. How these properties vary, is called periodicity. Yeah. I just wanted you people to know what periodicity means. And that is all. Don't just learn topics whose meaning you don't know and whose cause you're not aware of. So, those properties of elements that change as you move from one element to the next, maybe to the next, more to the right, to the next, down. Those properties are called the periodic properties, such as their size, which size is not an accepted word, and the accepted one is radius. How these properties are changing, those things of saying so and so increases down a group, so and so decreases across a period, that thing of change, that thing that describes the change of these properties in either directions is what they call periodicity. Periodic properties are the properties. Periodicity is that description of how these things are varying or changing or differing. Hope that is okay. So with that, I think I can now. People forgot to take this screenshot. People, please don't forget, anything to do with screenshots is serious. I don't want us to lose our work and you people start crying. Okay, so you take that screenshot, then we go through our notes very fast. Yeah, we are supposed to complete this subtopic today. So the things are very easy. So they are saying, what are those common ones? By common, they mean there are so many, but the common ones, meaning those ones that are usually examinable. That's what common means. So by common, we mean usually what? Usually examinable. Okay. Now, we have atomic radius, and because of the word atom, because of the word atomic, we are dealing with atoms. So what if we are dealing with ions? It's called ionic radius. If you're there and you still have issues concerning atoms and ions, then, excuse me, then you have a very big task. There is a lesson we recorded last holiday where we did break down an atom, a molecule, element, compound, and ion. I don't recall which lesson it was, but I want you to, if you really have issues with those words, I want you to go and check. It was mole concept. Yeah. You can check under mole concept, which is topic 1, senior 5, term 1. Under mole concept, you will find it under that topic 1 of senior 5, term 1. So the other common properties that we are looking at today, and not any other day: ionization energy, electron affinity, electronegativity, electropositivity, metallic character, and standard electrode potential. This standard electrode potential shall push it. So I will say pushed it to topic 10. Someone may be like, what is that topic 10? Topic 10 is called electrochemistry. It is just here, not verified. It's here. Are you seeing that topic? It's the very topic that begins senior 6 term 2. But you need to have this planning. It is planning that makes people pass. Not a lot of content. Just have a proper plan towards you getting the target points. That's what we used to have those days. Just have a plan that no one knows. So topic 10, it is electrochemistry. That's where we shall find those things of standard electrode potential. Even the word is here. You know, Ugandans believe by seeing. So you see that word of electrode potentials? After talking and defining it very well, that's when we shall also talk about its what? Its periodicity. So when I don't talk about it and give it to you as research work or take home assignment, don't feel bad. I've told you why. So in this session today, we are going to take our time and understand these things from scratch, understand the real chemistry and basics. Whether we complete at 10, 11, midnight, 1, 2, 3, I'm not leaving, not until we get done with this whole document. We are just on page 8 out of 26 pages. We have just started. Okay, now those are the ones. Just do this, Have it in mind. Atomic radius is with ionic radius. Ionization energy is with electron affinity. Electropositivity is with electronegativity. Metallic character is alone. Standard electrode potential odd man out because it is in a further topic. Just like that. Atomic radius, ionic. Ionization energy, electron affinity. Electropositivity, electronegativity. Metallic character on its own. Standard electrode potential odd man out. Why? It's in a further topic, period. Now what are they saying? They are saying that all those atomic properties we have just listed, or the periodic properties, are affected by 4 factors. And these factors were mentioned. 4 of them. 4 of them. 4 of them. 4 of them. You are given nuclear charge, shielding effect. Shielding effect is the same as screening effect, electronic configuration, and they are talking of atomic radius. No one will tell you to list the 4. It is always very hard. They always just ask you to explain. Usually you explain trends. As you're going to see this very document we are using, in most cases you describe trends. For those of you who have covered the topic, you know how these questions are set. They give you a table with values to explain. But what usually disturbs people, where do I start from? How am I supposed to write this? How do I write my explanation? Like, why a table and how are you going to... I don't know. It usually gives students hard time. But let's try our level best and see if something can be really done. Okay, now you're going to come across other terms, but let's first concentrate on knowing what each means. What does nuclear charge mean? These letters you're seeing in brackets are letters which are there to show you how these things are denoted. I'll tell you why it is Z. Then the shielding effect or screening effect is that. Most of you know what we call a screen. A screen is something like that, is something that shields. Yes. Now, you know what they call a sunscreen, especially those people who move a lot in the sunshine. You know what they call sunscreen. You apply it on your skin and it shields you from those effects of maybe tampering with your skin, something like that. So screens are always there to shield. So screening effect, shielding effect. So they are not two different things, they mean the same. Electronic configuration, this one was taught. Get the point? This one was taught. So I don't expect it to be a problem. Atomic radius, it's one of the things we are going to talk about today. So stay on, listen carefully. Because guess what? We are now going to break down the factors. If you fail to break down the factors which affect the atomic properties or the periodic properties, that means you will not even understand the atomic properties. So understand the factors that affect them first, or understand the atomic properties first. Also understand the factors which affect them in form of definition, then later connect the two. That is why I like this topic. Look at factors alone in their own caliber. Talk of atomic properties alone in their own caliber. Now connect the two to bring out the periodicity. Period. Get the point? Okay. The first one is nuclear charge. Before I explain nuclear charge, I want you to recall this. When I was teaching you that very topic of electronic configuration, I remember telling people, actually I was teaching you both mole concept and electronic configuration. I remember giving you something like the structure of an atom, those who recall. Then after I gave you the structure of an atom, I gave you the notation of an atom. And I give you something like this, A, Z, isn't it? Those who recall. Then we said that this A is what they call atomic mass. We even said that it is either atomic mass or mass number. That's what we said. Then I remember telling you that this Z was a small z. Those who covered with us errors, you know that's how small z looks like. Or some books leave it as capital, no problem. This is chemistry. They don't care, they care less. And we say that this one down is what they actually call atomic what? Atomic number. Isn't it? Then we said, you listen. Then we said that atomic number usually represents the number of what? The number of protons. Everyone knows that. Then after saying that it represents the number of protons, we asked ourselves, what is really present in the nucleus? What is really present in the nucleus? I want you to listen. At one point, we drew the nucleus. We drew the nucleus and we said the nucleus has protons. It is also having what? Neutrons. Then we said these protons carry a positive what? Charge. Then we added on and said that these neutrons we say they have no charge, isn't it? Then we said because of that, we added and said the nucleus has a net. Net means after all other present charges have been cancelled. So if the nucleus has two things, protons and neutrons, but the neutrons have no charge and protons have a positive charge, that is very clear. That is very clear beyond doubt that the nucleus has a net positive charge. So if you people are good at English, I want to put here a very simple statement which is very correct. If we are saying the nucleus has a net positive charge, we are talking of charge of the nucleus. Charge of the nucleus. Charge of the nucleus. Charge of the nucleus. Someone can say nuclear charge. Isn't it? You understand? We're just playing with the English. Someone has said charge of the nucleus is positive. Then for you can change the language and just say nuclear charge. They are still the same things. So what I want you people to appreciate is one, that the nuclear charge is related to these protons. Nothing much. I don't really need much from you. That's what I want you to appreciate. That the atomic number, which was represented by what? Z, shows number of protons, which protons are related to nuclear charge, which is the charge of the nucleus. How are they related? The charge of the nucleus is positively net. But why positive? Because it has protons which are positive and neutrons which have no charge. So there is a way the charge of the nucleus is connected to protons, and there is a way protons are connected to Z, which represents the atomic what? Number. Why I'm giving you that connection, I want you people to appreciate why nuclear charge is denoted with this letter Z. So it is not just out of the blue, but it's because of some relationships. So that is the family tree that connects letter Z to nuclear charge. And you all know nuclear charge looks at, okay, it is positive. It is positive connected to protons, it is letter Z. That's all you need. It is so hard for people to ask you definitions. And I told you, don't stress yourselves with definitions until the form of assessment is out. At least first understand, even when it comes out right, that you people will define. Don't be bothered. After all, you know the meaning. The moment you write the meaning and it really makes sense, you get your marks. So, when we read this definition of nuclear charge together, let me see what these people have. So you read this definition. If you read it and it makes sense, I'm going to be using the same technique of explaining. But if you people say it's not getting into the head, then I will change the mode of teaching. So they are saying this is simply the total number of positive charges where in the nucleus of an atom, full stop. What did they add? It is equivalent to the number of protons, and it is denoted by which letter? Z. So if it is 100% very okay, you write for me that comment in the chat. 100% very okay. 100% very okay. That's what I'm going to base on to either change mode of delivery or I maintain. Okay. Okay, most people have given in their comment and they have said 100% okay. So that is very good. Now we are going to go to the next thing, and so I believe nuclear charge is no problem at all. Now I want to talk about the shielding effect or the screening effect. Very important concept. Now, you people should appreciate a very simple fact. Should appreciate a very simple fact that the nucleus, you see, the structure of the nucleus is something important that you shouldn't take lightly as far as this topic is concerned. I assure you, if we give these things the time they deserve, no concept in periodicity will give you a time. No concept at all. So, you people have realized that now, if this is our nucleus, it has a what? Positive charge, or what we call the net positive charge. Something like that. Someone may be like, why are you putting there so many charges? Because it's not that a nucleus only has one proton. It has so many. So I just put those just for an example. Then you all know that around the nucleus is this one, but you all know that around it, we have what we call orbits. Which orbits? Someone can call them shells, electron shells, energy levels, sub-energy levels, but I'll talk about that at the right time. So what am I really bringing to you are these electrons. These electrons which are always here. Now, because these electrons carry a negative charge, negative charge, negative charge, negative charge, negative charge, there is always that force of attraction. You get? That's the force of attraction I want you to appreciate. Yes, that's what I want to talk about. Then I will say, because of the difference in charges, because of the difference in charges, because of the difference in charges, so what? The nucleus always attracts the surrounding what? And that's what they call the nuclear attraction. That's what I wanted to tell you. So I wanted to bring out that new word, nuclear attraction. So when we mention it again, don't be confused. Simply understand it how that the nucleus we are talking about has a net positive charge. The electrons that are surrounding it have a what? A negative charge. So there is always that force of attraction. Attract, because the charges are unlike. So that's what they call nuclear attraction. So when we talk of nuclear attraction, get it that way. However, 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 the surrounding electrons, may, have said may, so not always, may be shielded. You know what shielding means, eh? So yes, we have agreed that those electrons are always what? Attracted because of the difference in charge, so that attraction exists. But sometimes, however, those surrounding electrons may be shielded. Shielded, if not shielded, someone may use prevented, or someone can straight away use screened. From the nuclear attraction. That is it. That is it. Yes, the attraction exists, but sometimes those surrounding electrons may be shielded or prevented. And this phenomenon, should get used to these words. So this phenomenon is called the screening. It's called the screening effect. And we just agreed that screening effect has another word, shielding. But we shall be using screening effect in our explanations. That's why I had to prioritize it. So how do you bring it on board? How do you bring this phenomenon into existence? You tell someone the nucleus is positive. The electrons surrounding it are negative. There is an attraction. However, that attraction may be blocked, may be screened, may be prevented, may be stopped, may be shielded. And that's what they call the shielding effect, or more modernly, the screening effect. So we have seen that the electrons are being shielded from nuclear attraction. So the biggest question is, who shields? If you answer that, then you'll be the best student in chemistry in the country. If you can literally answer who actually shields, then you are a very good student of chemistry. Who shields? That is very important. Who is that person? Who is that person doing the shielding? Who is that person doing the shielding? Hmm. Hmm. Anyone to give it a try? I'm going to consider a metal, then a non-metal. Yes, I'm going to consider a metal. I'm going to consider a non-metal. So the metal I'm going to consider is going to be calcium. You know it is 20. Then the non-metal I'm going to consider is chlorine. And you know chlorine is 17. So if I happen to try drawing the O-level structures, but this one is too big. Let me use magnesium so that the space is enough for us. Whatever we are explaining is lifetime. I really don't want you to reach upper schools, engineering school, medical school, and you be totally confused. I don't want you to be the most confused fellow at the faculty of medicine. Even you are going to become teachers. You're supposed to be competent. So don't cram these things. Don't, please. Especially teachers, these are the very things you're going to teach. Whatever you're going to be taught at campus is not what you will teach. Never. Then those who are going to become doctors and engineers, whatever we are doing, we are brain shaping you so that your brain can literally have that sense of bringing out concepts the best way. You get? So you gotta be patient. So who shields? We are going to consider metal and a non-metal. I've chosen magnesium and chlorine. The other ones are unlucky. Why would we deal with unlucky things? So I'm going to draw the O-level structure. It had the nucleus. It had that. It had that. Then that. And even this side. I want to do the same thing. I think I need to start teaching art. Yes. So let me make sure the nucleus is distinct. That is the nucleus. So magnesium, you all know, in O level it was 2 to what? 2 to 8 to 2. Then you all know that chlorine was 2 to 8 to 7, isn't it? Because that's going to guide us on how to draw this. Then if we come to illustrate, this is our nucleus. So the nucleus, I'm going to put inside positive charges, just to show you it is our nucleus. Just a sample, 3 of them only. Then we shall start the drawing of the electrons. You know, here there are only 2. I'll show those. Here there are 8. Yeah, like that. Then the last 2. So I can put one here and another one there. Then we come here, same thing. Hope those who can are taking notes. So here, this side, there are 7. So if I show all of them, the 4, and I begin pairing the 5, the 6, maybe 7, like that. Those are the 2 atoms. One thing you're not supposed to forget is the real electronic configuration. I want you to respect it. Yeah? The one S2, this one I taught you well. 2s2, 2p6, 3s2. And you should also not forget the one of chlorine. 1s2, 2s2, 2p6, 3s2, 3p5, that one. Now, the question is whose shields? You understand? When you look at, I want you to look at that thing very well. When you look at this one, I think this electron. Remember, we are looking at I don't know whether people are still aware that when I talk of shielding, the nucleus is here positive, and our electron is somewhere here with its negative charge. This is the electron. So what we are calling a shield in this topic is anything which is going to occupy this position. I think this position. That's what we are calling a shield. I'll put the simple word there, shield. The nucleus, the electron, anything in that area is our shield in this topic. So I want us to consider that electron I've circled in green. That one. Even here it is present, it is here, this one. I want us to give these energy levels. I want us to give these energy levels letters. Or let's give them numbers to make things easy. Let me use black. So here the first energy level I'm going to give it 1. The second I give it 2. The third I give it 3. Even here, the first one I give it 1, 2, and the third 3. Get the point? Now I want you to look at that electron I've circled in each case. Who is shielding that electron? Who is shielding it from nuclear attraction? Who can tell us? Who is shielding that electron from nuclear attraction? Who is shielding that electron from nuclear attraction? Who is shielding that one electron? Who is shielding it from nuclear attraction? So someone has said nothing, and it is right. So that electron is shielded by none. Good. Shielded by none. And it is right. You get? So even this one the same, because they are the same, they are on the same energy level. Even that one none, even this one none. I've put them in green. Now I want us to handle another one, and let me use red. Let me use orange. These ones. Are you seeing those ones? Those electrons. You tell me, who is shielding them from nuclear attraction according to our diagram? Who is shielding those electrons? So those electrons are representing all these ones in orange. Just because for us we have decided to consider one, but it is representing all those ones in orange. Who is shielding those ones in orange from nuclear attraction? Someone has said the first one, first energy level, good. shielded by 1. Good. Very good. Of course, you know we are shielding from nuclear attraction. We go. Now this one. What of that one? Mm-hmm. Mm-hmm. Who is shielding that one electron? Mm-hmm. Who is shielding it from nuclear attraction? That one in that color. Who is shielding it? Yeah, you people know a lot of chemistry. And is shielded by 1 and 2. And that's all I wanted. The good thing you have realized that. So I have a simple question. What is common? What is common to 1 and 2? That's what now I'm going to teach you. What is common to 1 and 2? So one thing I want you people to realize that 1 and 2 are energy levels. 1 and 2. Both of them are energy levels, that one we agree. And one thing so special about them, they are completely filled. That is very important. They are completely filled. You understand? Completely filled is very important. But some people decide to use the other word of fully filled. It is also okay, but me, I prefer the word completely filled. Then one thing I want you to also realize, that an electron is shielded by an inner shell. Yes, you must put that into consideration. What do we mean by inner shell? That if this is the nucleus, you're having this and this, and maybe you're having your 1 electron here, and this one was full, the first one. Realize it is full and inner. So that's what I mean by inner, that this is the electron we want to shield from nuclear attraction. This is the electron we want to shield from nuclear attraction. So this shell that is shielding it from the nucleus is actually inner, because it is more next to the nucleus than actually the outermost energy level. So that word inner is very important. The word energy level is very important. Completely filled is very important. And usually the electrons they concentrate on are usually outermost electrons. But that shouldn't scare you at all. The word outermost it shouldn't scare you at all. It's not a big deal. But this electron, if it's on the last energy level that is outermost, yes. So the word outermost, if we come across it, it shouldn't be a concern. Outermost. Yeah. Now, the other important thing is this. All level, this is what you people do. This is what people do. People set 2 to 8 to 2. Of course, I'm talking of what? Magnesium. Then when we come to advanced level, people say 1s2, 2s2, 2p6, you get 3s2. You understand? Hey. Then, what is funny? It is very clear that that 2 belongs to the 3s. Even these first 2 electrons are belonging to the 1s. I think you can see. Remember, this is what represents the number of electrons. So you can see those 2s, those ones are sorted. But when you look at this one, 8, it is supposed to be in a single energy level. Are you listening? It is supposed to be a single energy level, which is complete. But when you come to A level, we split it. And that's why when we split, you call this a sub-energy level. Even this one, you call it a sub-what? Energy level. But both of them make up a complete energy level. What do I want to bring out here? That when someone says 2 to 8 to 2, and they say this 8 is completely filled, and they say, remember the 8 is the energy level. According to L level, the whole of it is the energy level. Completely filled energy level. That's what you people know. But then someone may come out and say, but if you're really saying that 8 is a completely energy level, but in actual sense, it is made up of 2 sub-energy levels, that is 2s2 and then 2p6. You all know S is always stable or full with 2 electrons. So this one is also full. And this one is always, the P is also always full with 6. So it is also what? Full. Why am I showing you this? I want us now to replace energy level with sub-energy level. In that, every time the energy level is full, that means even the sub-energy levels are full. Do you people agree with that? I don't know. Do you people agree with that statement? Let me put it here. That if the energy level is full, if you claim that the energy level is full, me I'm saying that also means that the sub-energy levels are full. Some people call them shells. People call them sub-shells. It is also okay. People, is that correct? That when you claim that the whole energy level is full, that means even the sub-energy levels that make up that energy level are full. Is it right? Okay. Now, if you've gotten that, I now want us to go. I don't know, people are starting to get issues with network because I don't expect anyone to be dozing off because I alerted you earlier that we are going to have the long session. Okay. Now, we are now going to go and look at the definition of screening effect in peace. You now know all that information. Actually, first take the screenshot before, I don't know whether we took this. Before you take that screenshot, we take the next, then we read the definition of screening effect together. You can also take that. Now we can read it. We can read it and see if things are making sense. Okay. If there is anything unclear, we say it. They are saying the shielding or screening effect. So this one just simply represented by S, maybe because of the word screening, maybe because of the word shielding. What are they saying? They are saying this is the repulsion. We talked of all those words: repairing, preventing, screening, shielding, stopping of the outermost. I told you that when you come across the word outermost, you shouldn't be confused. They are shielded by those, you understand? Of course, sub-energy levels and energy levels have electrons. So electrons are repelled by electrons. Do you now get it? That what these, if this is the nucleus, you're having an electron here, and also what you want to shield is an electron. So because of the negative charge here and the negative charge here, this is why they are using the word repulsion here. So that repulsion happens. You get the point? By the innermost. We talked of that word innermost. And then here they are using sub-energy levels. Get the point? That when the energy level is full, even the sub-energy levels are full. So interchanging the wording is very okay. Yes. And the mere fact that they are innermost, that is clear that they are full because they are inside. No one has tampered with them. So someone may be like, where is the word full or it completely being used here? It hides in the word innermost. And they are repelling them or stopping them from nuclear what? Attraction. That was explained. They are saying electrons in an atom shield each other from the pull of the nucleus. Why? Both of them are negatively charged. So there is that repulsion. And in the repulsion, this one that is inside, this one will shield this from nuclear attraction, period. They are saying the more you shield, the more you reduce the nuclear attraction. Isn't it true? Because you're shielding from nuclear attraction. So the more you shield, you're reducing the nuclear attraction. But they are saying it all happens with an atom with more than one energy level. You've looked at our illustrations. All of them, we dealt with 3 energy levels. Of course, you realized if you use only one energy level, the current electrons will be shielded by none. So that's why here they are saying more than one energy level. That's when shielding starts. We go. Then what else is here? They're saying the greater the number of energy levels, the greater the shielding effect. You just understand this. Why? You all know it's energy levels that shield. So if energy levels are of a great number, expect the shielding effect to also be what? Great. That is obvious, eh? From just normal understanding. It is obvious. It is obvious. Now, people, let me hope this one is okay. So is the meaning of shielding effect okay? Those simple words. Trust me, when we get this, things are going to be very easy on our side as far as the future is concerned. I'll just give you a break. We get back. If you don't get back, that's up to you. Me, I will proceed with those who will be on. Is the concept of shielding effect okay? We go to the next. Okay, now let us explain something very important. Something very important. Let me first save this. Okay. Now let us look at this battle. Just look at this battle where nuclear charge is versing screening effect. I want us to realize something so important here. So we have in case 1, we also have in case 2. In case 1, this is what we have. I'm going to come and show our nucleus in red. Like that. Now, let me first show 2 electrons, as usual, 2 electrons, 2 electrons. And here we also have 2 electrons. So let's assume outside we just have only and only one electron for both, but they have that difference in the number of energy levels. Now, there is that thing they call effective nuclear charge, and it's what I want us to look at. There is that thing they call effective nuclear charge. There is that thing they call effective nuclear charge. Effective nuclear charge. This one means how effective, just like you hear it, how effective is the nuclear charge. How effective is the nuclear charge? And I'll tell you, this is told from the battle. This is told from the battle below. So it is the battle below that is going to finish up everything. We really want to know, how do we really tell this effective nuclear charge? If we are to tell how effective the nuclear charge is, we tell from the battle. So what happens in the battle? It's what I want us to realize here. So we are having case 1, and our goal is to shield this electron. I want someone to, we have two things. This nuclear charge, I want you to understand these things. This nuclear charge looks at nuclear attraction. You get the point? Or just simply attraction. Then the screening effect looks at repulsion. That's why we are calling it a battle. That nuclear charge really wants an electron to be attracted to the nucleus. But the screening effect or the shielding effect shields that electron from nuclear attraction. So its thing is repulsion and not attraction. That's why we really call it a battle. So I want someone with very good English to raise up their hand and tell us that in case 1 or case 2, either that electron in green is attracted more by the nucleus than it is repelled. And whether you're getting it. Who is repelling? Screening effect. Who is attracting? Nuclear charge. So I want someone to just say that this electron is attracted more than it is repelled, or this one is repelled more than it is attracted. Anyone? Just using those illustrations. Which one do you think is attracted more than it is repelled? Which one do you think is repelled more than it is actually attracted? Yes, Alice. Yes, Alice.
Yes, good evening, Master.
Alice, you couldn't unmute. I don't know why. Yes, Blair.
Me, I think in the first case, there is much force of attraction than in the second case. Since in the first case, like the what? The yeah.
So case one is more attracted to the nucleus, then case two is more repelled from the nucleus. Yes.
Yes, I think both of you got it right. Even those who tried in the chat, that is it. When you look at case one, it is only one energy level that is repairing, and the electron we want to shield is so close to the nucleus. So chances are high that we shall have some sort of attraction. But when you look at case two, it is far away from the nucleus, very far from the nucleus, and those energy levels in the middle are fully filled. So they can do the shielding very well. For reasons I explained already. Therefore, shall come here and say, electron is more attracted is more attracted than repelled. Of course, who attracts the nucleus? Of course, who repels? Innermost electrons. I just don't want to overmake them a point in our explanation. The keywords are repelling and attraction. Then when we come to this case, things are different. Here, is more repelled. Is more repelled than attracted. So the good thing here is that who repels, you know. Who attracts, you still know. So I will not say much about that. Who attracts, you know. Who repels, you know. Than attracted. Goes by the nucleus. Now, I'm teaching these concepts for the last time, for the first and last time. Trust me when you get these simple statements. By the time we begin explaining how they work, how they affect everything. Trust me, things are going to be obvious. So you gotta listen so that you enjoy most the end of the lesson. Now, where do we have nuclear charge less effective, and where do we have it more effective? Because effective nuclear charge, we said it asks how effective nuclear charge is. A nuclear charge looks at attraction. So here where the electron is more attracted by the nucleus, this is where effective nuclear charge, or this is where nuclear charge is more effective, isn't it? So here, shall say, nuclear charge is more effective because attraction has overpowered repulsion. It's more effective. And because of that, we come out with a conclusion and say effective nuclear charge is higher. Effective nuclear charge is higher. Effective nuclear charge is what? Is higher because of that reason. Here, repulsion has overpowered attraction. So this time around, our nuclear charge is not so effective. Why? Repulsion has overpowered it. So here we shall say nuclear charge is less effective. It's not so effective. Yes, the attraction may be there, but again, repulsion has overpowered. So that means it is less what? Effective. And because it is less effective, the most important statement is that effective nuclear charge that effective nuclear charge that effective nuclear charge, that time it was higher, can say is less. I don't know, someone can say lower. And these are the statements we are going to be using. They're the ones we are going to be using. So to add on a few words, when you listen, when the electron is attracted more, you listen, when the electron is attracted more by the nucleus than repelled, we always say nuclear charge outweighs screening effect. But remember, here we are still dealing with the English of the chemistry. When time reaches where we are supposed to write the real words, we shall see what should be written in your answer. But meanwhile, agree, when we are having more attraction than repulsion, that means the charge which attracts has outweighed the screening effect which repels, isn't it? That's when we say effective nuclear charge is higher, greater, or it increases. Whatever, we shall see that. Then here where nuclear charge is not so effective, that simply means it has been outweighed. That simply means the screening effect. That simply means that the screening effect, that means that the screening effect outweighs That means that the screening effect outweighs the nuclear charge. That means the screening effect does what? Outweighs the nuclear charge. And those are the words we are going to be coming across. So you better pick things from here and nowhere. Now, for us to tell how really effective nuclear charge is, you see, there is mathematics that is not so important in chemistry, but we may decide to apply it. When they talk of effective nuclear charge, you really want to tell how effective is this nuclear charge. How effective is it? For you to tell how effective it is, we shall need to get the nuclear charge that we have. We shall need to get the nuclear charge that we have. Remember, the top enemy of nuclear charge is screening effect. That as nuclear charge attracts, screening effect is repelling. So for you to tell how really effective nuclear charge is, we need to get what it can do and subtract what its enemy, screening effect, can do. Get the point? That is it. That is it. You really want to tell how effective nuclear charge is. Nuclear charge is Z. How effective it is, effective nuclear charge is Z with the subscript of EFF to mean effective. Screening effect, we agreed it is just sorry. So when you see that formula somewhere, don't be surprised. Just understand it in the English way. That for you to tell how effective it is, you need to get what it has done and what its enemy has done, so that you get the net. It's like the net. So because of this subtraction, it's like the net nuclear charge. What the nuclear charge could do after we have removed all the negative energy of screening effect. Because the two are enemies, why they do the opposite. One attracts, the other repels. So you people take that screenshot and as well comment about it. It starts straight away from effective nuclear charge. Let me tell you, this is all you need, and the thing is done. When we understand this, the other notes, you are going to be just going through them. We just define electropositivity there and then. We switched to these ones. So you people, this you should appreciate from that the moment effective nuclear charge is higher, that means even the nuclear attraction will be very great. Get the point? And you should even understand that when effective nuclear charge is less, that means the nuclear attraction will not also be so good. Those are obvious, and we are going to find them in the statements we are going to be dealing with. Now, we are going to go through our notes and see what we have under screening effect. We do other things. Okay. Effective nuclear charge. Effective nuclear charge, that's how it is denoted. I explained. They are saying it is the net. I've talked of net because somewhere we are going to subtract. It is the net positive charge experienced by an electron. You understand? Hey, it is what the electron finally experiences. The net. That's why I was like, it is this one that will determine nuclear attraction. Because it's what the electron finally feels. So this determines the final nuclear attraction. Because it's what we get after the screening effect has been removed. Okay, let's read through this statement. Using the formula, it can be interpreted that if the screening effect is high, if the nuclear charge is high and the screening effect is low, then effective nuclear charge increases. These are things I've been talking of. And this is just mathematics. Z minus 8 is equal to the effective nuclear charge. But when this one is very high and this one is very low, of course we expect this to do what? To increase. What makes them to change that way? We are going to look at all this. Just don't be worried. Those are just mathematical statements from the equation. And then they are also adding on and saying that when the screening effect is high, remember, it is like this, Z minus S. So they're saying when the screening effect is high and the nuclear charge is low, because it is a difference, then this one will also reduce. It will be left with no option other than reducing. Mathematically, it is very clear. Mathematically, it is very clear. Now here they try to show some illustration, and they said electrons outside have no effect on effective nuclear charge. You know the nucleus is positively charged. Electron of interest you can see. As simple as that. These are things we have been illustrating. Though for us we have been using local illustrations, but these ones are just bringing out whatever we have been illustrating before we made our statements. So the last thing, you people, let me assure you, the moment we get done with our atomic radius, especially the part of atomic radius, ionic radius will be your research work. That one I've told you point blank. I told you I'll always do for you 80%, then the 20% will always be yours. But if I leave for you only ionic radius among all atomic properties, after all it's ionic for ions, and what I'm discussing today it is atomic properties, but you need it too. I will have discussed 95% of the subtopic and left for you 5%. You people just make sure you understand atomic radius. It is atomic radius that is going to drive all the others. That's why I'm giving my simple concepts here time. Because I know when atomic radius finally comes out, well, we are good to go. We are good to go. Now, I want to take you a bit here. So please, you listen. We agreed this. We agreed when effective nuclear charge, I've just discussed it. So we agreed. The people were on. Listen carefully. When you understand atomic radius, all the other ones I'm going to be just reading notes. Trust me. But the problem is going to be one when you don't understand atomic radius. Even those of you who think you know, you don't know it. because the way you got it may not help you to understand electronegativity. And yet me, I really want us to be using atomic radius on all of them. So we gotta get this, and the rest will be easy for us. So we agreed that when this effective nuclear charge, 1 when this effective nuclear charge 1 is higher, then the other one will be is lower. We said because of this word effective, they mean the net positive charge or the net attraction the electron you want to attract feels. So if the effective is higher, that means nuclear charge is very effective. And when this is lower, that means nuclear charge is not so effective. So when it is higher, even the nuclear attraction is higher. Nuclear attraction, listen, even the nuclear attraction is what? Nuclear attraction is higher because it is very high. But what else? When the effective nuclear charge is lower, what does that imply? This one implies that even the nuclear attraction, when the effective nuclear charge is lower, even the nuclear attraction is not so good, it is lower. Because that means why effective nuclear charge is less or lower, nuclear charge wasn't so effective. Now, concerning attraction, assuming this is your, we have been doing these things and we have been representing our nucleus in red like that. Then I can draw this, I can draw this, I can draw that. We are having that. That is the electron I'm considering. When nuclear attraction is higher and when nuclear attraction is lower, when is this electron going to be pulled so close to the nucleus? People tell me. I have case 1 where nuclear attraction is higher. I have case 2 where nuclear attraction is lower. When is that electron in green going to be so much attracted closer to the nucleus? You're not responding to me. Where are we going to have that electron in green attracted closest or closer to the nucleus? Which case is going to make sure that electron we are attracting is closer or closest to the nucleus? Which case? Case 1, case 2. We have two cases. Case 1 where nuclear attraction is higher. Case 2 where nuclear attraction is lower. One of the cases, the electron will be so close to the nucleus. And in the other case, the electron will be far away from the nucleus. So I'm asking, which is which? Where is the electron closer to the nucleus? And where is it far away from the nucleus? People, the nucleus is attracting. I don't know if people can realize this. If the nucleus is over pulling this, over pulling it, over pulling it, over pulling it, do you know what is going to happen? Even this energy level will be pulled. Are you seeing that? Even that energy level will be pulled, will be pulled, will be pulled. And that energy level will be pushing these ones inside. And they also push. You see that? They also push. They also push. So in the due course, because of this very high nuclear attraction, that electron is going to be pulled so much. And as a result of pulling it so much, you know what happens? It pulls the energy levels just close to the nucleus. It pulls the outermost. Even the outermost pushes these ones inside and inside and inside. So the electron is pulled closer, is pulled closer, is pulled closer to the nucleus. And you people have realized, and as a result of just pulling it closer and closer, you can look at the radius of the atom reducing. Radius of atom reduces. Anyway, after all, I haven't talked about radius. Right now, I can just talk of size because it's what you're seeing. But you all know every time I'm going to be using the word size, I will be putting it in a box. And I put X to show you that it is not a chemistry word, just an English word. But of course, we need it to make these concepts actually come out. So realize when the nuclear attraction is very high, that electron outside, it will be pulled and pulled. So these energy levels will just come inward and inward, inward and inward. And the size of the atom will just be reducing and reducing. Get the point? Then when I come this side, I realized people are not good at these night lessons. Even after alerting people, people just go, each minute we are losing a participant. Each minute we are losing a participant. Anyway. So the other thing is that the electron, this side, because nuclear attraction is lower, we don't expect it to come so close because the nucleus is not pulling it like it has been pulling this one in case 1. So here we shall say the electron is far away from nucleus. Far away from what? From nucleus. And remember, for this case where nuclear attraction is lower, we agreed it is effective nuclear charge which was lower. And for effective nuclear charge to be lower, that means nuclear charge is not so effective. By the fact that nuclear charge is not so effective, that means the electron is getting more repelled than actually attracted. So because they are repelling it more than it is attracted, you know what repelling means. You know what repelling means. This explanation has been here. If I just try to show you what repelling is here, just show you something small. I'm going to just use those as sample electrons. This is what repelling is. That's the repulsion between those two. Do you see that when the repulsion continues, it's like this one is going like as a result of the repulsion, You're just pushing it, pushing it. Remember, this is our electron of interest, this one in green. I've circled it in green. It's what we are basing on. So if it is actually repelled so much, that means you're even pushing its energy level out, making it to go out, making it to go out, making it to go out. Because nuclear attraction is low, and it all comes from the beginning parts that is getting repelled more than we are attracting it. So that repulsion is what causes that electron to be ignored, pushed away, pushed away. Remember, it is attached to the energy level. As you're pushing it away, you're pushing away the energy level. Pushing away the energy level like that. You're just pushing away the energy level, which is something very bad. Pushing away the energy level. You get the point? Now, because of that, the size will be reducing. So it will be increasing. Size of atom is just increasing, but size is not a good word. Size, of course, will increase. But that's it. That's it. That's it. When we answer these two remaining questions, we are going to be halfway the session. What makes the following to increase? We are talking of nuclear attraction increasing and what? What makes the following to increase? First one, nuclear charge. You people, we agreed nuclear charge is Z, and it is charge of the nucleus. It is charge of the nucleus. So this one is our nucleus. You get the point? It's our nucleus. Then this one is a positive charge, which represents protons. Isn't it? And guess what? For me, what I think, since nuclear charge means charge of the nucleus, and the charge of nucleus is positive, which positive represents protons. For me, I believe increase in number of protons. May I believe increase in number of protons for may I believe, let me use the exact words, for may I believe increase in number of protons. What's not happening? Increase in number of protons does what? Increases. What does it increase? Nuclear charge. And if you people know, number of protons is atomic number. And you all know atomic number, we represent it with letter Z. These are things that are just connecting and obvious. So atomic number is that number of protons. If it increases, we agreed, even nuclear charge will increase because those two are connected. So every time you see an increase in number of protons or increase in atomic number, just have it in mind, nuclear charge is what? Is increasing. So I want to show you something here from the periodic table. I want us to use the periodic table. When you look at this periodic table, I'm going to extract out something small. I'm going to extract out this part. Are you seeing this part? If you're passing it, this one. No, the whole of this, this one. It's what I'm going to extract out. That one. Sodium, potassium, magnesium, calcium. It's what I want us to use. Said I'm extracting out sodium, which is 11. Then here we have magnesium, which is 12. Potassium, 19. Of calcium, which is 20. So I want us to consider, are you seeing? These are protons. Those are protons. These ones are protons. Those 19 are protons because that is a position for atomic number. These ones are protons. You are all aware. So when you look at that periodic table of ours, as I move from sodium to magnesium in the same row, that is across a row, which we agreed to call across a what? Across a period. Then we shall also consider maybe magnesium to calcium, just that. Or sodium to potassium, same thing. And we say this is what they call down a column or down a group. Isn't it? So if you people realize that when I consider these are 11, these are 12. So there has been increase in what? I would say number of protons increases. Number of protons increases. Then when I also look at magnesium to calcium or sodium to potassium, what do you realize? 12 to 20, same thing. That down a group, this has been across a period, the number of protons increases. But also down a group here, we have also realized the same thing. That the number of protons increases. Get the point? Now, what are you noticing? Every time protons increase, we have agreed we expect nuclear charge to increase. So either way, nuclear charge increases. Nuclear charge increases. Very important. But one thing I want you to realize that for across a period here, sodium to magnesium, it was only and only one proton. Shouldn't take that for granted. Yes, the number increases, but it was only one proton added. Get the point? Then here, there were 8 protons. Isn't it? Of course, even sodium to potassium, 11 to 19, they are still 8. So what else are you realizing that as you're moving across a period, you add one proton at a time. If you're moving down a group, you're adding 8 protons at a time. And the other thing I want you to appreciate that most configurations are always like this, 2, 2, eh? So we are not going to take this 8 for granted. You see, they are 8, eh? So in simple terms, we always add a full energy level of electrons. You get? I want you to follow well. I want us to reach the point of reading the statements in our notes when things are just making sense. But you learn the art first, the statements will come later. So there are 8 protons, and we have said, according to O-level configurations, we always have 2 to 8 to 8 to 2. So that 8 and 8 mean that the energy level is full, isn't it? So as you're saying, as one person is saying you're adding 8 protons, someone will say, it is actually full energy level of electrons. Someone may be confused and be like, hey, doctor, here you're saying electrons, but here they are protons. Then, my dear, you have forgotten the things I taught in mole concept. I remember telling you that the number of protons is the same as that of electrons in the neutral atom. And here we are dealing with neutral atoms, you can see sodium atom, magnesium atom, potassium and calcium atoms. They are neutral, like nothing else is attached to them. Totally nothing. Then the other thing you need to get as very good students is that these protons, let me teach people a technique. Do you know why people perform well in senior 5 and then in senior 6 they fail? Or why people's performance declines? It is usually because of poor foundation. I've really tried my level best to give you the best foundation in each and everything I get time to talk about. Why? These very things will come back in the future. At high school, at medical school, at engineering school, at whichever school. And the moment you start not getting things because of your poor foundation, things will really give you a time. But trust me, after these funny sketchy explanations, you can teach yourself the whole periodicity. Why? Whichever statement they are mentioning, we have mentioned. Whichever connection we have mentioned. Whichever trend mentioned. Okay. So protons, the other thing you should understand that protons are added to the nucleus because that's where they are supposed to be. So understand that protons are supposed to be added to the what? To the nucleus. That is it. That's where they're added. I really don't know now what people want. We have realized across a period, down a group, nuclear charge increases for reasons we have given. Down a group, since protons are 8, meaning electrons are 8, that means we are adding just a full energy level of electrons. And sodium to magnesium across a period, it is always 1 proton added. But that doesn't remove the fact that nuclear charge increases. That one I'm done. Now, we are going to consider the same thing. We are going to consider the same thing. We are going to consider the same thing and talk about screening effect. We are going to consider the same thing and talk about screening effect. And this is the consideration that can change your entire life as far as the subject is concerned. So just like I have no serious reminder, you take that screenshot, we proceed. I just believe we are so far okay. That one I will not ask. Because even if you say we are not, I have nothing to do for you. Take that screenshot. We talk about screening effect. Okay, now we are going to come here. Be like, okay, we had our sodium here. Said we are considering the same thing to now talk about screening effect. Which same thing, having sodium here. Then potassium here. Then magnesium here. Then calcium here, 20. So the other thing you people have to understand that in screening effect, we basically prioritize a full energy level. If you recall our illustrations, whichever was shielding was an energy level and it was complete. You get the point? So, and with shielding effect, we have some sort of repulsion. Who are we repelling? We are repelling electrons. Electrons are negatively charged. They can only be repelled by a ferronegative charge. So with screening effect, it's electrons repelling electrons. So as we are talking about it, we should put the word electron in our statements so that the meaning comes out. So when I come to talk about this, it is only one electron added. One electron added. You get one electron added, as you can see. 11, 12. This is 19. This is 20. So from sodium to magnesium, it is just one electron added. But let's look at here. Look at here. Here there are 8 electrons added. You all know this is down a group. Then you all know this is across a period. So here we have 8 electrons, what? 8 electrons added, isn't it? Now, we have said that these 8 electrons mean a complete energy level of electrons. They mean a complete energy level. They mean a complete energy level of electrons. That's when we've said it. So since you all know that what does the screening is actually a complete energy level of electrons, because of this word, those of you recall the illustrations, it was a full energy level that was doing the repulsion. Those who are copying notes, you can actually check and confirm. So because it's a complete energy level of electrons that has been added, we are free to say screening effect increases. Because you've added one more thing that is going to shield, so we shall say screening effect increases. Screening effect increases. Why a completely filled or a complete or a full has been added? But for this case of across a period here, it is only one electron that has been added. You very well know that it is not one electron that does the shielding. It is a complete or full energy level. So here the statement that we can say is that screening effect almost remains constant. Screening effect, because you know it's not a full energy level. It is not a full energy level. It is just one electron. yet it is a full one to do the screening. So here you may end up realizing that the screening effect is what? Is remaining almost constant. So their screening effect remains what? Almost constant. But if you don't use that word, people have another word. People may say, yes, it is the energy level that shields. But what does the energy level have? The energy level has electrons. It's them that do the actual shielding, if you recall, because shielding has sort of repulsion, which repulsion should be between electron and electron. Someone can be like, yes, it is a complete one that does the shielding, but this is just one Ka electron. We don't refuse that. But what if it also contributes something little as far as screening effect is concerned? I don't know whether you get it. Yes, it's a full energy level that does the shielding, but what is contained in the energy level? Electrons. So it is actually electrons that do the shielding. Because the complete one has 8, so we can make it better and say it is 8 electrons that are supposed to do what? The shielding. But here only 1 K electron has been added. What does that imply? That implies that someone can make another statement and say, screening effect, yes, will increase, but will increase only and only slightly. So say screening effect slightly increases. The moment you miss that word slightly, you cannot get any score. Slightly increases. Slightly increases. Very important statement. Slightly increases. That's what I wanted to tell you. So you people know what happens to nuclear charge and screening effect, both down a group and across a period. Now, after those, I'm now going to combine. But before I combine, I'm going to first pinch the screen a bit, and you tell me whether those two illustrations are okay before we actually combine, because combining is going to bring problems. I assure you. This sodium 11. This is magnesium. This is magnesium 12. This is calcium 20. These values are very important. But I don't know what's wrong with people. People say we should also start short lessons during the day. But the very people who suggest they don't attend. And what I've realized, and you also know that the biggest percentage depends on recordings from the drive. So why don't you people just leave me to have my long sessions, either in the afternoon or in the night? You leave me with that. I'll literally try and do my best. We shall cover the work we are supposed to cover. Period. And the work on the drive, most of you have 2 weeks or 3 weeks home. You are not going to complete that work. And that's what is really worrying me. But anyway, before I combine screening effect and a nuclear charge, first look at those two. Look at those two. 1 for nuclear charge, 2 for screening effect. Look at those two. Look at those two and comment. Are they okay? How they are changing across a period down a group. I'm waiting for the comments, please. Okay, let's now combine. Now, you all know this is across what? Period. This is what? Down the group. Now, hmm, we are all aware that in this direction, nuclear charge increases. Then here, screening effect. Only slightly. Isn't it? Then here, down the group, we agreed nuclear charge increases. Screening effect what? Increases. Isn't it? That's what we said. Now, for across a period, things are very easy. For across a period, things are very easy. Okay. Is across a what? Period. And this one is down a column, down a group. Okay. Now, this one is very obvious. How? Are you seeing this word slightly? Yes, both are increasing, but screening effect is only increasing slightly. You understand? That means only increasing slightly. What does that mean? The increase. Because screening effect only increases slightly, that means the increase in nuclear charge is greater than the increase in screening effect. Get the point? It is better, I repeat, it is better to read this symbol as greater than. It is better to read that symbol as what? As greater than. However, there are those that prefer it to be read as out what? Outweighs. But it's better to be read as greater than. Should write the spelling of greater well. It is E. Like that. Now, because the increase in nuclear charge is greater than the increase in screening effect, that means our nuclear charge is so effective. You understand? That means our nuclear charge is what? So effective. So effective. So if our nuclear charge is so effective, that means effective nuclear charge what? Increases. because we are talking of increase everywhere, eh? So even when we reach nuclear charge, we shall say increases. Effective nuclear charge increases. Then we said every time you hear the word effective, effective is like the net, like that force of nuclear attraction the electron finally feels. So it'd be like, effective nuclear charge increases, and when it increases, even the nuclear attraction increases, because it is the net feeling the electron gets from the nucleus. So nuclear attraction does what? Increases. You understand? Then we said when nuclear attraction increases, we talked of electron getting very what? Very close. And after very close, after electron getting very close, we talked of the size. But as said, size is not a good word. It is better we use radius. But because it is getting very close, the size is what? Reducing. But I say radius is better size. I think you see how now things are flowing. I'm starting to save time slowly by slowly. And by the time we begin reading the notes, everything will be very clear. Now, since in the first place, nuclear charge outweighed screening effect, that was for across a period. Here, it was across a period. Now we are going to explain down a group. Now, because of changing trend or direction from across a period to down the group, it's going to be tit for tat. In the first place, nuclear charge outweighed. Now this time round, screening effect is going to outweigh. You can get it that way in form of tit for tat. But in case you don't want that, you'd be like, both nuclear charge and screening effect have increased. Who is actually going to outweigh the other? And this is where the chemistry comes in. Remember, down the group, 8 electrons have been added. 8 what? 8 electrons. These 8 electrons, you all know, they make up a full or complete energy level. Full or complete energy level. Full or complete energy level. You understand? But for nuclear charge, it's normal. Yes, 8 protons have been added, it's understood. But this time round, screening effect is feeling like a boss here. Why is it feeling like a boss? That 8 electrons have been added and they make up a complete energy level, which complete energy level is what actually does the shielding. You all know from the illustrations we made that it is that complete energy level that actually said it is that one that actually makes, let me say, actually does. It is that one that actually does the shielding. It is that actually does the what? The shielding. Okay, because the screening effect is feeling like a boss here, there is something important. What is going to be the result of that? The increase in screening effect will hence outweigh the increase in nuclear charge, because for this time round it's the boss. The other time across the period it only increased slightly and it kept quiet. When you change the trend to down the group, it now gets to become the boss, simply because the 8 electrons you're adding make up a complete energy level which does the actual shielding. So I'll say increase So we have said the increase in screening effect outweighs the increase in nuclear charge. Outweighs the increase in nuclear charge. And the mere fact that nuclear charge has been outweighed, that is clear that it is not effective at all. It has been outweighed, so it's not effective. It is not effective at all, simply because it has been outweighed. And the mere fact that it is not effective at all, that means effective nuclear charge is actually less. Say that effective nuclear charge is less, so it actually reduces. And we all know when we hear the word effective, it is net. Why net? That's what the electron finally feels from the nucleus. So even the nuclear attraction goes down. Nuclear attraction goes down. And the mere fact that here the screening effect is the boss, so because we have said what screening effect does is what nuclear attraction does. So when nuclear attraction falls, you all know, screening effect is the boss here, and it is the lead of repulsion. So when repulsion gets too much, we agreed the electron will be far away from the nucleus. Far away from the nucleus. And being far away, I'll just write the word far away because we have it before in the workbook. Being far away, that means the size is just getting bigger and bigger. Size is not a good word. The right word is radius, atomic radius. So size gets bigger and bigger. But we shall later learn that size, the better word is radius, and bigger supposed to be larger. Yeah. Just like that, radius, but you also need the other words, eh? Then these ones come in later. So you people, that is it. I'm done with atomic radius. And we agreed atomic radius is connected to all the others. All of them, you like it or not. All of them are connected to atomic radius. And the very statements we've been making. So as you take that screenshot, put that into consideration. Atomic radius is done. Take that screenshot too. Okay. Okay, now I think we can go through the rest of the things, but have it in mind, all things have been talked about. Yeah. Now we are going to just read notes. So for the remaining time, we are just going to be reading notes, just that. Reading notes, it's going to be the order of the day. So if you've forgotten the simple concepts, I really pity you. Really pity you. Okay. Back here. So I'll also not hesitate to say something little about atomic radius, just something little. So you all know in math, radius is of a circle, of course, basically. That's a perfect one. So you always have the center here, and you all know that this is the radius. R. You get? That's the radius that most of us know. But unfortunately, most atoms exist in pairs. Yeah, most atoms exist in pairs. Most of them exist in pairs. Most of them exist in pairs. And what does that imply? That one atom will be here, and another one will be here. The other ones, we call them circles, but literally here we are talking of atoms. Hope I've tried. So a circle and its center. If the name changes to atom, then this one becomes the what? The nucleus. But if atom is circle, then nucleus is center. So assuming these are atoms, that is an atom, that is an atom, and then these two are identical because we have said they exist in what? In pairs. So they are similar but not the same. So they are identical. You get? And then each of them is having their nucleus. Their nucleus. Remember, they're existing in pairs. You understand? It is their nucleus, that is their nucleus. So we have this distance. I don't know if you people did circle properties in O level. But if this is the nucleus, let me rub this. Write the full word. Nucleus. Nucleus. So the whole of this distance from there up to here is what they call the internuclear distance. Is what they call the internuclear what? Distance. You remember when I told you intermolecular in alkenes, between molecules. So this distance is internuclear. Why? It is between this nucleus and this nucleus. Hence the word internuclear distance. Get the point? Internuclear. Between two nuclei. and it is of course a distance. Hope I'm clear. So if you have the whole of that distance d, but remember for us we just need radius of one atom, which is this r. But because most atoms exist in pairs, you may not get it like that. But at least you can obtain the what? The internuclear distance may be d. Internuclear distance d. So you people know math, that this is radius and also this is radius. They exist in pairs. All you can get is internuclear distance. But for you are looking for r. So according to me, r r that I need will be a half, or it will be that distance over 2. That internuclear distance over 2. That's when I can get the r. But as you know, mathematics, this one is the same as half what? Half of d. And that's the math you only need to define atomic radius. That's the only math you need. That's the only math you need. The other thing I can add on is the thing of existing in pairs. 2 atoms paired. So if we are having 2 atoms that are paired, they make up a molecule which is diatomic. You know di means 2, yeah? So the molecule we get is actually diatomic. So 2 atoms paired together, the molecule they give you is what? Diatomic. Ig, you know oxygen, you know chlorine, and etc. What do you know about oxygen to oxygen bond? Because this one is double. And what do you know about the chlorine to chlorine bond? Because this one, non-metal, 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 you all know that. I'm right to call this a covalent bond. I'm also right to call this a what? A covalent bond. You understand that? Hope you people, this thing has not confused you of R, the atomic radius being half of D, which D is this what? Internuclear distance. And this R is actually the radius of the atom. Radius of atom, or what we call atomic what? Radius. So you people first tell me whether that sketch is okay. Hey, you see all that? I'm doing all that just for us to define atomic radius. That's why I'm doing all that. I'm doing all that so that we can define atomic radius. And then you later reach medical school and find hard time defining very detailed concepts of biochemistry. That's what I don't want. So, is that sketch okay before we literally define it together? Is that sketch okay? Okay. I've said it is fine. So shall come here and say, so you look here and tell me if the statement is okay. I'm just reading it once. They are saying atomic radius is half the internuclear distance between 2 atoms in a covalently bonded diatomic molecule with similar atoms or in a metallic bond. Is the statement okay? Is the statement okay, or you need me to pardon? Is the statement okay, or you need me to pardon? Because to me it is very okay. It has all what we have been saying. Half the internuclear distance between two identical atoms in a covalently bonded diatomic molecule. Or someone can just say in a bonding situation. Someone can just say in a bonding situation. Just that. In a bonding situation. So this will be for those who will be making notes. Someone can put here two identical, or here they used similar. Then here someone just says, instead of saying covalent bond and metallic bond, someone can summarize that, provided here someone comes and they put identical or similar. They can summarize all this and say in a bonding situation. Yes, provided you come here and fix this word identical, because it was accompanied for here as similar. Anything can work. So that is the definition. These are the illustrations. Very obvious things. Okay. Someone is saying metallic test. It is the same thing. I told you they occur in pairs, even if it is sodium. Even if it is sodium, same thing. The point of occurring in pairs was enough for you. So that's why they mean by metallic bond, yeah? This one is a metal, then this one is a metal. But I've said you can ignore the covalent things and so on and just say in a bonding what? Situation, because all bonds are catered for. So you just need to say what? Have the internuclear between two identical atoms in a bonding situation. Hope we are understood there. No, it's not in contact. It's supposed to be in a bonding situation, not just contact. That is now English and not chemistry. Now, you people basically here they said the variation in atomic radius down the group. Here the best thing is to connect these two. Here the best thing is to connect these two and you get effective nuclear charge. But even talking about them independently, you can, but it is not advisable. But of course the questions are always clear, don't worry. It is better you combine the two and talk about effective nuclear charge generally. But don't worry, we have some sample questions here. Yeah, we have some sample questions here. And groups, both periods and groups were catered for. So we are going to be together. But we agreed anything to do with ions. You see these ions are not easy. Why? You're supposed to first review the lesson where I talked of the difference between atoms and ions before you visit this. But anything to do with ionic radius is for the student. We agreed I will always do 80 or 90, then the remaining percentage will be yours. The remaining percentage will always be yours. That is it. The remaining percentage will always be what? Yours. Now, where are we? We are still here, eh? Just generally, you look here. The higher the nuclear charge, the more strongly the outermost electrons are attracted closer to the nucleus, reducing atomic radius. Isn't that true? When nuclear charge is very high, that means the nucleus can strongly attract those outermost electrons, bringing them closer to the nucleus, and in the due course, size is reducing, atomic radius is reducing. Then the other one is the opposite, that the lower, that means the attraction is very weak. And when attraction is very weak, that means the electron, the outermost electron, the electron is getting far away from the nucleus. Hence the size is just what? Increasing. This is what I warned you about, and I'm now going to just be reading statements because I invested my time in giving you the right basics. Okay, now, let me see, where is Michael Blair? Michael Blair, you go to the, no, I don't want to disturb. If it is a girl, they will reply very fast. Let me see. Scholar. I don't know if Scholar is sober. Scholar, if you're sober, you go to the premium discussion group right now and ask those people why they are going off one by one. So that we confirm whether they are either dozing off, losing data, or losing interest. So you find out and give me a report. Because now we have reached the most interesting part where we are going to be just reading notes and proceeding. Okay, screening effect. The greater the screening effect, that means here the shielding effect is so much. Like the nucleus cannot over attract the outermost electrons. Like the repulsion is very strong. You get? But who are we repelling the outermost electrons? Repelling them from what? Nuclear attraction. That means these electrons are not so much attracted. They are weakly attracted. And they are far away from the nucleus. If they are far away and not attracted but rather strongly repelled, that means the size is going to get bigger and bigger. Now it is you to sit down and master how these statements are supposed to be written on paper. But for you to come out with a format of getting the statement into your head, you should know what each statement means. Then you later sit down, read, master it. That is my role here, to make sure each of the words makes sense, and then your understanding comes later. I told you here we just simply appreciate. You later read to understand. By the time you read the 6th time, you've mastered the content and you're good to go. But by the time, few people can reach the 6th time of reading. That's why it's a very hard level. Then we go to the lower. The lower the screening effect, that means even attraction is not too much. If repulsion is not too much, that means it is the attraction which is much. Like repulsion is not too much, so these electrons will be very near because you've not over pushed them away. And the attraction is strong. That could be our assumption. Following the fact that the repulsion is not much, that means attraction is actually dominating. And when attraction dominates, the electrons get closer and closer to the nucleus, and the size reduces. Which size is the atomic radius? So someone confirmed to me that those two are okay before we even combine them in a single question. Do you get those statements for those two? Okay, now combined explanation. Combined explanation. Now I want you to see this very difficult. Very difficult. Those of you recall our sketch, it is here. When everything was combined, do you see what happens across a period? Size will eventually reduce. That means across a period, atomic radius decreases or it reduces. But you're not supposed to cram, you're supposed to derive these points one by one. Even if you're good at cramming, please force your brain to understand. Please. Okay, now I'm going to just switch. I'm going to enjoy. They are saying atomic radius decreases from sodium to chlorine. So when they tell you from sodium to chlorine, that is of course across a period, across a row. And here they are dealing with period what? Period 3. So the periodicity we are going to be looking at in these questions is the periodicity of period 3 and group 2. Why? It is those two that are part of this topic. Remember, we're on topic 4. Are you seeing? We are dealing with topic 4, where the first subtopic is periodic table, what we are handling, and the other subtopics, we have group 2 and period 3. You understand? So we are going to be doing examples that are related to period 3 and group 2, so that when we reach these ones, we skip what we already discussed in subtopic 1. Hope you get it. So that when we reach these ones, we give more time to the reactions. More time shall be given to the reaction. It is the periodicity that is really hard, but we shall maneuver. Okay. Across a period, why is it like that? It's because from sodium to chlorine, nuclear charge increases. We saw that. Why does it do so? Because a proton, so don't forget this, a proton is added to the nucleus from element to element. You saw that. From sodium to magnesium, 1. From magnesium to aluminium, 1. From aluminium to silicon, 1. From silicon to phosphorus, 1. Like that. That's why they say from element to element. But there are some people who don't want to write element to element, and they instead put here is successively added. So when to some point you see this word somewhere, successively, successively in Luganda it's kanemu kanabili, one by one proton from element to element. So if you don't say successively, you can just say a proton is added from element to element. That one has been understood. Screening effect almost remains constant. But we said another word can be slightly what? Slightly increases. Slightly increases. Then, what are they saying? Because electrons are added to the same energy level. That's something I forgot to talk about, but I'm talking about it now. We say that only one electron is being added, and we are adding it to the same energy level. Look at this. This is what they mean. Sodium is 2 to 8 to 1. Magnesium is 2 to 8 to 2. You understand? That we have just shifted from 1 to a 2. That one electron we have added has been added to the same energy level. So we expect our screening effect to either increase slightly or that slight to be considered as almost constant. You get the point? So same energy level, that is the reason behind everything. Same energy level, and I think you can see the third, we add that electron still to the third. Even if you go to aluminium, you also realize that it is 2 to 8 to 3. So from 2 to 3, that one proton added, it has been still added to the third. So we don't expect screening effect to change too much. We only expect it to change too much when a complete energy level comes in, because it's what does the actual shielding as far as our illustrations were concerned. Now, because it remains almost constant but nuclear charge increases, The other statement is lacking in this explanation and it can cost you. So I will edit it and add it there. So before you say effective nuclear charge increases, you should talk about who outweighs who. So you say the increase in nuclear charge outweighs or is greater than the increase in screening effect. So that means it is nuclear charge. Okay, that means effective nuclear charge has been so effective. That means effective nuclear charge increases. And we agreed what effective nuclear charge does is what nuclear attraction does. What did we say? Outermost electrons get closer. Don't you know that? More strongly attracted. Don't you know that? Than repelled. Don't you know that? So that's what I said. That my role today is to make sure whichever word will appear in the explanations of our notes, you have the idea. So that it's now you to sit down and look at how answers were written, how they are going to go into your mind. So you're just simply appreciating and making sure the concepts are flowing. Later on, give them time, connect them, stick them to the mind, period. And before I forget, I think people, I don't know, but I don't think you guys took this screenshot. You take that. You take that screenshot. You also take the next. I think that was forgotten. Okay, so that is it. So people, let me hope that explanation, the combined one for atomic radius is okay. So anything to do with ions, that is your research work. Why? You're supposed to visit first the lesson of moral concept, where I gave the difference between ions and atoms, and you also have to visit that of electronic configuration, where I talked about the configuration of ions. So even this one, anything to do with ions, that is going to be your research, and it will take the 5% of the first subtopic. For me, I'm covering 95. We have agreed anything to do with ions is your research, and it is covering that. So that is research, and you will take that 5%. For me, I'll do the other percentage. Anything to do with those ones? Now, this was for the group, yeah? Remember, the other one was period. I told you, whatever we are going to be doing, there is period, there is group. Now, you know, according to what we know, as far as our summary is concerned, you look at that. Down the group, what do we have? We are having size increasing. We called it size. And we are supposed to get these things from one by one as I explained them. Yeah, but I'm very worried the way people are reducing in number. It's alarming. And I'm really disappointed. You people, we have a lot of work to cover. So these questions already say state the trend, yeah? So this first statement, you're seeing that atomic radius increases from beryllium to barium. It is very okay, and it is the statement. So this is the stating. When they say state, they expect a statement first. So that is the statement. But I advise you to begin with this here. That is say, from beryllium to barium, atomic radius increases. Don't ask me why, but I've told you begin with the atoms. Why? Even if you're describing a graph in biology, x-axis, y-axis, we always quote these values, and be like from A to B, this is constant. You understand? So it's better to begin with those atoms. From beryllium to barium, atomic radius increases. Why? Because because nuclear charge increases. Why does it increase? You know, protons are added. Where are they added? To the nucleus. They are saying screening effect also increases. So at this point, when nuclear charge was talked about, this is very correct, but they never talked about why. So you have to add it on your own. Why? Because of protons getting added. Where are they added? To the nucleus. Screening effect increases. Why? Because they're adding an extra energy level completely filled with electrons. We said that, isn't it? Because we said 8 electrons are added. Which 8 electrons make up what? Which 8 electrons make up a complete energy level? You get the point? So, you all know, because it is an extra energy level that has been added, screening effect feels like the boss here. And after feeling like the boss, it outweighs or is greater than. That the increase in screening effect outweighs the increase in what? Nuclear charge. And you know, when nuclear charge is outweighed, it feels small, so it is not so effective. And the mere fact it's not so effective, effective nuclear charge is left with no option other than what? Decreasing. And what effective nuclear charge does is what nuclear attraction does. Since it has decreased, even nuclear attraction gets weak. And when it gets weak, electrons cannot be close because they are not going to be strongly pulled, but they will be so far away because the attraction is weak and the repulsion is too much. I don't know. So your role is to just make sure you can reproduce the same statement because you know the behind the scenes of everything. So I don't want you people first tell me before I go to the next thing. Does that statement make sense to you? Right now, things are supposed to make sense, but you're not supposed to be in position to reproduce the statement now. That one can never happen. Right now, you're supposed to just make sure whichever is in that statement makes sense to you. So does everything in the statement make sense? Do you appreciate that later on you'll be in position to reproduce after you have read? Okay, that is good. Anything to do with ionic? By the way, people, I'm disappointed, yeah? That is the fact. That's because I don't want to be pissed at you people who are on. But I'm disappointed, like... Anyway. But you're making me to overthink at a time when we are supposed to do serious business. Anyway, when you look at this document, we are now on page 12 of page 26. You first tell me, are you seeing that? Are you seeing that we're on page 12 of 26? I don't know. Is that seen on the screen? Is that visible on the screen that we're on page 12 of 26? Can you see that? Yeah, that is good. If you can, the last page is having assignments. So that means we have covered 50% of this. So you people have it in mind that it is atomic radius which is going to help us explain all these things of ionization energy. But you people are not easy. I cannot say, let's have a premium night. I tell you as early as 2 p.m. Then you log on when you're next to 50. But then now, every 30 minutes, we are losing a participant. That means, and the concepts I'm going to that are supposed to be explained next are very serious concepts, and they are the ones that give people the most hard time. People are just reducing in number. You're now 11. That means by the time I'm done with ionization energy, there are going to be 8 out of experience. Now, when I reach electron affinity, things which are very sensitive, how many people are going to be here really? How many? People, you are not easy. I really hate it when I deal with very unserious people. Because me, I want to cover these things and get done. But all I know, live lessons are good in that there is something you benefit when you interact with the teacher lively, which I can do. How I wish I had not told you that it is a premium night, then I would have the guts to proceed. But after telling people we have one, and then people leave, that's a total disappointment. That's why next week I want to find ways of getting you some other teachers who can handle your seriousness, so that me So you people, I'm back. Sorry for that. It was a glitch in network. You see, when the network decided to go off after it realized you people are giving me the hardest time ever. I don't know, but I hate that unseriousness. Yes, people depend on the drive, I agree, but that doesn't mean that you dodge lessons or you don't comply when we plan. Now, facts or truth be told, I'm not happy. I'm not happy, and for me, I hate dealing with unserious students because my pain is seeing a student failing even when they could pass. I think, anyway, that one I've told you. I'm going to get one topic to be handling that. I'll get any topic so that I get some other teachers to be teaching, because getting continuous disappointments from some of you may not be nice. Because I even gave you work on the drive to watch to give me feedback by today. That is chemical equilibria. None of you said anything in the chat. Sometimes I be here and I even want to tell you my stories. So many things happening outside the world. So many things happening at medical school. So many things that are going to happen to you in Form 6. I have all those stories because so many students have been confessing at various occasions. But when I look at what we are supposed to cover, I worry and be like, let me sit and concentrate, let's push. But I may be in the push alone. I may be pushing alone. Something I don't really want. The thing is, you people have made me lose morale for this session. You cannot begin when you are next to 40. Yet we agreed it's an overnight. And by 11, by 11, people were in teens. They were 19. Just 11. Yet I thought we are going to push up to 5 and complete this work. But all I know, even if I say we push up to 5, there are those who will still have to revisit. So for me, I'm going to be okay with what you people want. We have the short sessions, but if we don't complete the work on time, we shall complete it next holiday. Or I will cover it with the scholars so that when you're back in third term, the whole work is there. I will not stress myself. After all, you people are leaving me in the endurance and perseverance, something I really don't like. So the good thing, we have managed to reach the 12/16, which is 50%. So we've covered it. So what had to be one session has been split into 2. So when I put a lesson tomorrow, don't complain, because I was not supposed to teach tomorrow. But when I put there a lesson on Sunday, anytime, just to make sure I cover my 100%, don't complain. That is the deal. Otherwise, it will be next time that I will handle the remaining 50%. How can I really be prepared for such premium night? I bought my fruits, I bought my drinks, only to be having 10 students. What's that? And 5 are dozing and are quiet. They are not even hearing that I'm quarreling. That is the end. But I have no kind word. I don't have any kind words for you, semi-candidates. Otherwise, have a nice time. So next time, we shall begin with ionization energy. Then we shall go to electron affinity, as you can see. And these are our notes. You see, now how do I even get that hard to give you my very organized notes? How? Who does that? Ionization energy is a very long concept. Then we go to electron affinity, and there I would be. Just imagine electron affinity is on page 20, and it comes after ionization energy. And just 6 pages, 5 pages. After affinity, we look at electropositivity and electronegativity, and we end with metallic character. Just that. And the thing is done. We have period 3, we have group 2, but you people are not cooperative. The students who listen to this in the future, maybe 2 years, 1 year from now, you please forgive us for the currently unserious people. And the people who listen to this recording in the coming years, 2026, 2027, I hereby report to you the students of 2025 of new curriculum who are not focused, who are unserious, who take things lightly. Otherwise, we really thank God for the moment, and we thank Him for the life, for the health, for the happiness, for the academic atmosphere, for the academic relationships, and so many things He has provided. For His grace is unconditioned, and we pray for the same things. Yeah. May His grace keep reigning, and we pray all that, trusting His mighty name. Amen. So, I'll sign out. I'll sign out as Dr. Paul. I'll sign out as Dr. Paul. Mulago, College of Health Sciences. MBCHB is the source code. Those who want to visit more of our work, you can literally go to our website. But I will never forgive you people for spoiling my morale for a premium night. I wish it was a lesson and I never communicated that is a premium night. But alerting, just know, I started quarreling when we are 15. Now people are 12. People don't care. So that is the contact. That is the contact. And you kindly use the WhatsApp call to reach out to me. It's better. But one thing I advise before the lesson ends, my simple advice is that make sure you understand atomic radius well. Because it is atomic radius that really defines all those. So make sure you understand. Make sure you understand. Make sure you understand atomic radius very well. Make sure you understand atomic radius very well. Very well. For the remaining 50%, for the remaining 50% makes sense. Okay, at least we've covered 50% of a subtopic. Not bad. That's my simple advice. Otherwise, what you've done is very bad. Yeah. Making a tutor lose morale for a premium night. Quite absurd. So you take that screenshot, we leave this place. Those who have tried their level best, thanks for attending, but always advise your friends to act accordingly. and disciplined. Yeah. To the okay, you people, bye. Thanks for attending. Not quarreling to the innocent, but the guilty ones will listen to this. For you guys who are all now okay, but that's why I'm sending you to advise your other friends. But I'm going to organize the topic outline well. I'm going to give you an overview anytime from now, so that in case we get delays, at least you have an overview and sense of direction of getting academically out of danger. Yeah. Bye-bye.